components in the system. This is heavier than the easy trip.
Heavier than what?
This is the heavy in the whole system. It's heavier than the maximum boiler. You need to know that one.
No, I know. I was just
Heavy's the only stable.
right now. I was just gonna write that.
Heavy's the only stable. Trainer.
Now we have a choice.
You gotta do the binaries and first.
Wait, no, that's a set of it.
I'm going to do what we have to if I didn't click here now. Pseudo click. I'll let the class give the hints to everybody. I see people who aren't working on it. I'm guessing you're not working, so you don't know where to start. What's the first thing you got to do? Okay, so the yes, actually the final thing, it comes after the yes, yes and no. So the first thing is, can that and trainer be used to make two separate product streams? And if no, why not? If yes, how? Okay? What's the first thing you got to do? Go ahead.
Draw the arrows.
And then the whole thing is called, yeah, it's just residue. Okay, how many people have residue curves for this step? All right, start there.
So we have two different regions.
many distillation
You're
meters?
either heavy or you're either way.
How many distillation meters? Let's see. How many people say one distillation meter? You must vote. I'm going to say, how many people say one? How many people say two? Okay. How many people say three? Four? It has two.
What?
I'll draw it with you in a minute. Does that help you answer, yes or no?
Unstable now. Saddle point. Go next. Unstable. And then it makes it distillation boundaries.
Let's do the residue curves together. Okay, so I'm going to make sure here you go. We're working on the same residue curves. So I'll leave make a faint outline of whether you think it's yes or no now based on what you've done so far without me telling you anything. Okay? Yes or no? Can you do it? Can you not do it? I'll ask you the official one that I want you to vote on after we do the residue curves. Okay? Let's do this quite simply. Going from the entrainer to the maximum boiler, which direction? Up or down? Down. From the entrainer down to the heavy? Down. From the minimum boiler to the heavy? From the minimum boiler to the light? Right. And from the maximum boiler to the light? Up. Okay, so what are my pure components? What's the light entrainer? Unstable node. What's the heavy component? Stable. Stable. What's the light component in this system? Saddle. Now, we all do the N1 is equal to 1 in this case, so N2 is equal to 2 plus B plus, minus N1.
Why is that
Did I do wrong?
Isn't it two?
one? Why is it two?
Yeah. Equal planing gets you somewhere. Okay. And is it plus or minus? Minus 2 times S3 plus, no, this is N3. I should do it from memory. Let's do it right. Minus 2 times N3 plus 2 times S3 divided by 2. In this case is equal to 2 plus 2 minus 2 divided by 2 is 1. So how many nodes do we have? And how many saddles do we have? 1. Because we have a saddle and a node. Which is which? Someone be brave. I know you've all been thinking about it. Which is which?
The minimum would be a no because it's the lowest temperature in the system.
The minimum is a node because it's the lowest in the system. Meaning, what kind of node is it?
Unstable.
Unstable. Thank you. Making the maximum what? What does this thing look like? Go ahead. You want to tell me how it looks?
Oh, yeah. So, the minimum boiling intro. So, you would have a line that would go over to the light, and then, or you have one going directly to H,
Yeah. Okay.
and then you have one that would, go over to L, up to the maximum boiling, and then down to H.
Got it.
And then, you have from the trainer, you'd have one directly down to H, and then one that would go to the maximum boiling over to H.
Okay. Which makes us so it's pretty apparent that there's what?
Boundary.
Boundary between where and where, correct?
The heavy component and the maximum boiling.
It's not curved. I just drew it that way. Okay. Actually, let me draw it. Let me not draw it curved. I don't want a curved one. There is a real system, but actually that's a curved azeotrope there. But I mean a curved boundary. I don't want to. There's no way that you know that. So we have a boundary like that. Region 1, region 2. Now we're all on the same page. Don't raise your hand. Just in your head. Did you get the residue curve right? And you'll see in just a second how important it is to get these right, because it's going to allow us to ask that important question. Can that trainer break this azeotrope? Okay, so now make your vote. Will it work? No. Just write it, I'm gonna ask, I'm gonna do a poll. 10 seconds, let's take it on to write it down. Write it down in the margin. Can you do it or not? The question is, can you use this in training to separate that feed into light and heavy? Okay, how many people say no? How many people say yes? Okay, we just got to vote. I saw a lot of non-voters. Okay, let's try this one more time. Get a hand ready, okay? How many people say no? How many people say yes? Okay, who said no? Who feels like defending it? Go ahead, why no? Okay, can't get a saddle point. How many people said yes? Why? You feel like defending it? Yes, go ahead. Okay, oh, go ahead, yeah, go, sir. I was looking at him, but go ahead, please, go.
So you add the entrainer, which moves the feed up, because it's gonna have the same entrainer in it.
Yeah,
And then, so once you're up in that region, it's gonna go, down, you're gonna have a line going, like your mass balance line,
yeah. So
going across through the heavy component, and then up to,
I'm going to draw this. This is good. Okay, so you're like, say here,
yeah, sure,
okay? And then you're saying there's a mass balance line come from here,
yeah, and then going up to the,
okay?
so your heavy component is gonna be your bottoms out of your column.
That's right.
And then the distillate's gonna be the composition on that line.
It's going to be this stuff. Tricky
Yeah.
question now. Now what?
And you put it into another column,
You put it into another column.
and you're gonna get the maximum boiling azeotrope out of the bottom, and
Yeah.
the light component out the top.
Beautiful. Okay. Okay, so this is what she said. Do you feel like describing that again? Okay, because that was exactly right. There's only one little part that it's actually not wrong. There's nothing wrong. You'll see there's even something even more clever that happens, okay? But just, all right. So you don't get you confused. I'm going to do that mass balance again on a new triangle. All right, so we have a distillation boundary here like this. This is our heavy, this is our light. Here's our feed, here's our azeotrope. Okay, here's our entrainer. What she said was, first add the entrainer. We have heavy and light. So now we have heavy, light, and entrainer in some space like that. Okay? Then she said, draw mass balance such that the thing that we produce is the heavy out of the first column. Then, so this is column 1. Take the distillate, put it into a second column, and now which side? Where does the light come out? This one. You were right.
It is,
Comes out the distillate. Okay? So at this point, you're looking pretty good. Coming out here, we're going to have the heavy, light azeotrope, right? Because we're going to get this material. Here's the mass balance for column 2. Okay? But now, of course, it's something we all like to do. Yeah, say it loud, that's right.
Recycle.
Recycle. But there's something wrong, right? Okay, but the simple question is, did she correctly separate heavy and light using that entrainer? Does it work to that extent? It does. Yeah, go ahead.
Isn't that the white in head? I mean, the white in.
You're right. I'm sorry, it's a light entrainer azeotrope. You're right. Thank you. Thank you. It's important. It's this azeotrope here. So this is the light entrainer azeotrope. Here is the heavy light azeotrope. Any ideas? Go for it.
You just put it back into the second column,
Put it back to the second column. Where?
right into the distillate of the first column, because since you have
Well, you're gonna end up you're gonna get stuck, your mass balance won't work. You gotta get rid of that somehow, yeah?
Hazarding a guess, you could put it in as a secondary feed of thought.
Of the what?
You could put it in a secondary feed higher up.
It's a guess, unfortunately. It's actually easier than that, yes.
Throw it in that mixer?
Throw it in the mixer. Wait a second. So you're saying just put this in here. Let me give you some, just think about this for a second. What if I erase this? Instead of in trainer, what if I just let this be easy trainer? Okay. Whoa. What was that? What does that mean? What does it change about this mass balance diagram? If I add, I'm sorry, LE, I'm changing the one, but you get the idea. What happens if I add the feed to the ELE, let me make this. I think this is your diagram, and I'm messing with it. What happens if I mix the ELA azeotrope and the feed? Where am I going to be in space? So instead of mixing this way, we're going to mix like this. How about instead we just mix to there? And what are we sending round and round? Are we sending the end trainer round and round? What's going round in our recycle? What's going round in the recycle?
The azeotrope.
The azeotrope. Does it work? I mean, feasibility-wise, does it work? So what's the one thing that you can notice about distillation boundaries? In order for distillation to separate components, where does the feed and all the products have to be? Kathy?
Within the region.
They all have to be within the same region. Okay? So in this case, if you wanted to answer this quickly, but always be careful of rules, because I'm going to show you how to break them in just a second, okay? So I'm going to show you the rule and break it in the same lecture, okay? But if you have distillation regions, if your feed and your products are all in the same distillation region, you can do distillation to separate them. How to do it takes a little bit of thinking, but it's doable. Does everybody understand? Tell me your name, I'm sorry. What's it? Justine. Did everybody understand Justine's logic, how she got to her solution, which is 90% of this? So we got how she did it? Just make sure you can do it yourself. Okay, any questions on this? All right. A couple last things on homogeneous. I'd like to start heterogeneous today. So, a couple of things we've been assuming, I just want to show you in a little bit more detail. So, I've been taking it for granted that simple distillation is similar to continuous distillation. Okay, just so that you're all on the same page with the terminology here, simple distillation versus continuous distillation, okay? They're not exactly the same. Compositions are changing with time, compositions are changing with space. Steady state, batch, okay? We do residue curves with drawing, warp to time a simple distillation system. Does it really stick with continuous distillation? I've been assuming that it does, which I'm not going to change. I just want to give you a little bit of why, okay? So, for the simple distillation case, we wrote that the change in liquid composition in the still as a function of warp time is given by the difference in composition between liquid and vapor compositions. Okay, that was simple distillation. For a staged column, instead of it changing with time, everything changes in space, because everything's steady state. So we actually have things changing in location, right? So the composition in a binary column, a ternary column, is changing in space in our stages. And how does it change in space? It's by our mass balance, which is, at least above the feed, a top operating line, which we've written many times now. Okay? But it's a little hard to see how those two equations look like each other, even though they do, and I'll get there in about 5 minutes. It's a little easier in a packed column. Now, we've been talked about packed columns, and this is going to be the only time I'm going to talk about them. But you can actually do distillation without stages. You can do distillation by taking a cylindrical tube, putting in packing material. Did I do the packing material thing for you in 110? I think I probably just, did I take that out in the creativity section where we design packings? I've been done with that for years. Okay, all right. You can actually do distillation, and the height of this column is actually now in real height in inches or feet or centimeters. And you can get what's called a theoretical stage. You can actually relate it to stage separation. I have to tell this story, and I hope I don't get anybody arrested for it. But if you really want to make high purity ethanol, you can go to the Tiny Commons. I was taught this by my separations professor, so I have to share this story. All chemical engineers need to know this, in my opinion. Broken ceramic plates are great packing material. I'll leave the rest to your imagination. Right? Okay, got it. All right. You need a condenser and a boiler. It's got to be sealed. What do you make the tube out of? Buy it at the hardware store. Just get a PVC pipe, okay? I know how you're going to shine. Don't tell me. Okay. So that's a packed column. Now, the operating line in a packed column looks like that, like this. The change in the liquid composition as a function of height is given by the liquid composition minus the reflux ratio times the vapor composition plus x. Oops. That's an x. X of R. Okay, where H is the height in column. So as you go up and down this column, you can relate the liquid composition to the vapor composition using this equation. And you can see that this looks very similar to our top operating line. It's just continuous rather than discrete. Remember, this is discrete because we're counting stage 1, stage 2, stage 3. Here we're just going in continuous height. But it's the same equation. If we're at total reflux, in other words, R goes to infinity. Now we can build an R goes to infinity column, believe it or not. You just take all of your product and put it back down the column. Make nothing, okay? In fact, when you do see your lab, oftentimes they run it in total reflux. As frustrating as it might be. The point being that you can go and build a column total reflux. What happens then is as R goes to infinity, this goes to 1, this term goes to 0, and you see that dx dH is equal to x minus y. Does that look similar to something up here? Hopefully, it should look like this. So the height in a packed column at total reflux, the position is exactly the same as warp time. They can be translated from one to the other. Okay? So you're going to have a transition from the liquid to vapors, from the heavy to the light components in the column, just like you do in a simple column. So if you were running a packed column in a ternary space and you're looking at the residue curves, the liquid compositions would exactly lie on top of the residue curves. Okay, so that's how they relate to each other. Does that happen all the time? Okay, for the staged column, coming back here, at total reflux, so as R goes to infinity, total reflux, again this goes to 1, this term goes to 0, so you get that yn plus 1 is equal to xn. If you now discretize this, you don't have to worry about what I mean by this too much. We're just saying, as we change height, so xn plus 1 minus xn, okay, so liquid composition at the stage above to the stage minus, over the change in height you're going to have, which is just the stage height, it just equals xn plus 1 minus yn plus 1. So for a single stage, you could see that this is very similar to that term. This is a dx dh, where instead it's just delta to the discrete stages. It's the difference between the liquid and the vapor. Okay, so the profiles in the single feed continuous distillation column at total reflux will be constrained by simple distillation values. We write that down. Okay. Which is what we've been assuming all along. I told you, and I asked you to believe it. Of course, when you're not exactly at total reflux, you've seen this yourself. The profiles don't exactly lay over on top of the residue curves, but they're very close. And for the most part, they're still constrained by the distillation boundaries. Okay. So in order to go just a little bit more, and this is again mostly descriptive, there's not any problems I can do with this. I just think it's important to talk about it. Let's just talk a little bit about feasibility. And feasibility in the book, so you can kind of figure out where I'm at, is covered in both chapter 4 and chapter 5. So for a second, I have to bounce back to chapter 4. So when I say chapter 4, I mean ternary distillation, so no azeotropes, just so you can understand this for a second. So you have to go back in time, take away azeotropes, no residue curves. Well, let's just talk about the ternary distillation system. Okay? So we're going to do a simple column. We're going to have a heavy, an intermediate, and a light. And we've talked about this in words. In fact, I've asked this as a question. The bunch, so a lot of people this is kind of right. Okay? Just kind of think back to direct and indirect. What's the one thing I can't get as a product? With the simple column, now you've now seen, the last time I talked about simple columns, you had no idea what another kind of column was. You've now seen an extractive column which has 2 feeds. We're not talking about extractive 2-feed columns. Okay? We're talking about simple column, single feed, 2 products. Which of these can I not get as a product? Yes? The intermediate. Okay? So would it be fair to say that intuitively, you know there's a zone of products up there that you just can't get? This is, I'm going to make this more accurate in a second. I just want you to, does this make sense to everybody intuitively? You can't make the intermediate. We know we can make the heavy as the bottoms. We know that we can make the light as the distillate. But how are we going to get the intermediate? If we can't get the intermediate, let's just say that we have a feed in the middle of the column, in the middle of the space. Is there another region of compositions that I can't get as a product? Again, intuitively, and I'll show you how to a little bit more precision in a second.
A mix of the heavy and light.
Mix of heavy and light. Is that what you're going to say? Yes. So there's another zone down here. That's what you meant? I didn't even know who answered the question. Yes. Is that what you meant?
Yeah.
Right? So you're probably thinking of somewhere in there on the line. But you imagine still is a bubble there that you can't get to. Now, just so that I'm not going to do the derivation. The derivation's in the book. I'm just going to show it to you. But does this intuitively make sense? Because this is actually all you really need to take from this part of the lecture. You can't make intermediate, you can't make something that's between heavy and light. And so the derivation for this, which I'm gonna skip, basically involves making the worst possible column ever. And that's not the way the book describes it. When I asked Malone, he said, that's not how I would describe it, but it is what it is. Okay? If we take a column and we make it so that it only has a stripping section. So it's just a stripping column. So the very top, stage N, we're going to put the feed into N. Okay, so it has no rectifying section. Okay? Why is this important? Because what it'll do, now I'm going to look at what's going to happen down here. Remember, no azeotropes, no residue curves at this point. We're just going to go back to ternary. I want to blow up that region. Do you remember we made an Excel spreadsheet to plot these liquid composition profiles? Remember that? We made these ternary profiles. Did anybody play with the composition? So what I mean is this. If I tell you I'm blowing this up a lot, okay, because I have chalk, so I can do whatever I want. So there's 98%, there's 99%. And I'm going to look at 99% pentane, hexane, heptane, okay? C5, C6, C7. So I'm going to stipulate that we're going to make 99% pentane in the distillate by direct column. Do you remember what happened if you if you said it was going to have too much heptane in the distillate? In other words, the sum here is 1% heptane. So this has this looks like this. This vector looks like this. 4.010. So this is all pentane and hexane, and this is all hexane and pentane and heptane. But do you remember as we started lowering this, saying we're going to get more and more heptane? In other words, you see that I've got more heavy than intermediate in there. Do you remember what happened? At some point we had a saddle point, but at some point it became unfeasible. Do you remember that? We got an infinite number of stages. Do you remember that saddle pinch? Well, it turns out there's a point where you just can't go any farther. And I don't know where it is for hexane, heptane, pentane. So how do we find out where that is? We use a column like this, which basically says, I'm now going to make the most amount of heptane in this product that I can, because I'm not going to have a rectifying section. And I'm going to look at where that is. There's a proof, because it turns out these are all collinear, and there's a way to do it algebraically. I'm never going to ask you to do it. It's just a line you then trace, and you get to draw a picture that looks like this. But here's the thing I want you to know. How do I know where that point is? It's because it's the most amount of heptane I can have in the distillate and it still works. Does that make sense? You can't imagine this. Can I have more heptane than hexane in that distillate? It just doesn't make sense. Okay? So at some point it just doesn't work anymore. Where that is, let's plot it. So if this is our feed, and here's our distillate composition. Remember our intuition over there? It turns out that that edge goes right into the corner here. And it comes out kind of a curved shape, like that, for a direct column. You can now do the same thing for an indirect column, and it traces a shape like that all the way into that corner. This is describing this region, which intuitively we understood exists. It's impossible to get these mixtures of heavy and light in our distillate. Okay? So this is not feasible down here. Oops. And now to figure out what the rest of the shape looks like, all you need is a straight edge. Because if we're allowed to make material here and here, the highest purity composition we're going to have upper space is just drawing a line straight here from the distillate through the feed, and it forms this kind of bow tie shape, like this. And again, from the bottoms through the feed, straight up. And those lines are just given by the mass balance. Okay? Because we know we can make anything here, try drawing a line from this point through the feed. It's going to end up over here. So the farthest this line can go is this bottom composition there. The farthest this line can tip up this way is this down here. So your region of feasibility has this bow tie shape. And there's a derivation you're never going to do. It's more important you understand what this looks like. Okay? If you draw a line basically through the middle, like this is the direct split. And what's going to happen, is this the distillate or the bottoms from a direct split? This region down here. Is it the distillate or the bottoms from a direct split? These sets of compositions all down here beneath this line inside this feasible region. Distillate. And then, so these are the direct bottoms. Okay, what's this region here? If that's the direct distillate, the direct bottoms, what are all these compositions in this space here? What's that? Are they bottoms or distillate? Bottoms. Direct or indirect? Indirect. So these are all the bottom. And then, so these are the indirect distillate. So the point here is this for your feed. Those are the compositions that are possible. How do you know where that line is? All I want you to know is it has a shape similar to that. Okay, that's enough. Which is basically where we started. Do you see the similarities? It's just defining where the edges are. That's all. And I don't need to spend a lot of time talking about how that's formed. It's not really that interesting. The thing that was probably not intuitive is this kind of touch of the feed here. These two regions. And they're probably a little bigger than you thought. So that's all distillation can do. It can only create products. So the first column could only produce products in there. Obviously, we were able to make the other product in the second column, right? Remember we did that. Why did I put that at this part in this lecture? Because, first off, let me show you if we have a different feed, very simply. If you have a different feed, say we have a feed way up here. Here's our feed. We end up getting this funny looking bow tie. Looks like this. Like that. And so, there's our feed, our feasibility. Okay? Now, what happens if we have a system like we had before, where we have a residue curve like this, with a distillation boundary. Okay? If you now put all of this that we've done in today's lecture together, let's say that we've now got to add this entrainer, and we now have this as the feed. What does our feasibility region look like? With a simple column with that feed in that system with that distillation boundary. I'm now adding this material from chapter 4 back to our homogeneous azeotropic. Any idea, anybody want to guess what the feasibility region looks like with that feed, with those components? This is the same as the puzzle at the beginning, by the way. I just gave the entrainer on a different, the azeotropic different spot. Anyone want to guess what feasibility looks like? I guess it's all you can do. You can't tell me exactly what it is. Yeah.
Would it be a similar curve from the bottom right to the bottom left?
You mean like this?
Yeah,
Yeah, that's right.
and then you would do the same straight lines from ZF to the corners, except you just stop at the distillation boundary.
Good. And then this one goes up like that. So in fact, just stopping is all you need to know, which is what you assumed anyway. Okay, so these are feasible products. Why is that important? Yes?
I have a question. Is ZF meant to be the maximum point on that curve?
No, it's not. I skipped a point.
Okay.
Okay, it turns out that it's not, and it turns out that this, maybe you shouldn't have asked this question. The point where that line crosses like that is YF, which is if you have a liquid saturated liquid feed, the feed that's in equilibrium with it, that point there, you connect those two and that defines this line, which is the transition split. But it's just a definition. Okay, it doesn't actually have a lot of physical meaning. It's just that if the transition is defined this way, it means everything above it is indirect, everything else below is direct. But it's just convenient. Are you ever going to make a product like this or have a product like that? Most of the time you're going to be trying to maximize. You're going to be in these corners. Okay, just especially here where we're trying to go high purity products. Yes, it's useful. There's some column somewhere where economically it's profitable to make something that's less than pure. But most of the time you're making high purity products, right? So it's why not spend a lot of time. It's just a definition. Okay? But yes, there's a maximum between those. Okay. And then here's the last part. Okay. Every time I do this lecture, and sometimes I skip it and sometimes I don't, and I decided this year was important. This thing take away, okay? Feasibility is defined by distillation regions and this kind of feasibility curve. Nothing here should be different than what you already basically understood, you just never saw it drawn like that, okay? And remember, this is based on that same idea that in continuous distillation are profiles defined by simple distillation boundaries, okay? So that's why you can't go beyond it, which is, I can't remember who answered the question, one of you in the front here answered that correctly, okay? I'm just going to mention this because someone may tell you at some point that it's possible, and it is. Okay? Sometimes, and only by experimentation will you ever know this. So if you have to sketch a curve, there's no way you'll know it. There are curved distillation boundaries. Distillation boundaries look like this. Now it turns out that instead of being a strict boundary in continuous distillation, they form what's called a pitchfork distillation boundary, which means that this is the boundary for this region here. And this is the boundary for this region, which means there's an overlap. Now, of course, there's an overlap. The student that's thinking a lot and going, okay, wait, I can use that. I can make a product that's in here for one column, and then have another column that has a product that uses it as the feed. Yes, you can. Most of the time it's not used. It can be very susceptible to stability. Okay? I just want to make you aware that it exists. For this class, however, if you assume that, you're fine. Okay? The only way you would know, it only happens with curved boundaries, the only way you know that the boundary was curved was by experimentation. And it's still not a very wide region. So this is the exception. For the most part, just believe this. Okay? I just want you to be aware of that. There are some systems that were designed to utilize this, but for the most part, it's not used because it's susceptible to instability. Okay? All right. I want to move on. Yes, question.
When you have the two straight boundaries, how do you determine, or what's the guideline for like what the slopes of those should be?
For which straight boundaries?
The second triangle.
Here, these curves?
No, what about that?
These.
Straight lines.
Okay,
How do you-
so this line is that
is
the
it
rule
always going
line.
to be that slope, or can it be steeper, or?
Well, it turns out because this is curved, it's going to be always curved above that line. The farthest, so if you're taking a point, imagine a rule, with a ruler. I wish I had a ruler in this class. You think about this for just a few minutes, you'll see this. Try it with a picture in your book. Take that point, put your finger on there, and let this rotate like this, okay? Here's your mass bounce, you leave a rule. Take any point in this space, and if you continue that line, it's always lower. The farthest that slope is going to be in that direction is right at the high purity distillate.
Okay.
Which is why you just connect that pure component straight up through.
Okay.
It's not a rule, just try it. That's what it has to be.
Alright.
okay? It's just like kind of a logical progression, okay? That's a good question. Any other questions? I'm going to move on to heterogeneous, which is more complicated, but I'm not going to go into it in as much depth. How do you feel about homogeneous azeotropic distillation? Can you pick trainers? Can you do residue curves? Those are the key things. Do you know how a heavy entrainer works with extractive distillation? Didn't talk about it today. Those are the things to remember. Okay? Bullet, make sure I know that. Okay? Extractive distillation, residue curves, trainers. Okay? All right. So I'm going to move on to heterogeneous. I'm going to start with binary heterogeneous. The reason I'm going to do that is because ternary is the most interesting. Ternary is like why benzene separates ethanol from water. I find it fascinating, but before I can explain that, I want to show you binary. And the fact that binary even works is pretty neat, okay? And binary gets us to talk about immiscibility, because you probably haven't thought about it much. And we're going to use it for heterogeneous, and then we're going to move into liquid-liquid. Okay, so I'm going to go back to phase diagrams. So we have to kind of go back. And remember how I did all that work in chapter 2 where we talked about VLE, we had to review VLE in order to get into separation, so we have to go back to phase diagrams. So a homogeneous azeotrope which are the ones we just were talking about, minimum boiler on a T XY diagram has this appearance, which you're familiar with, where the minimum boiler is there. Okay? There's a minimum boiling azeotrope in a TXY diagram. Hopefully I've drawn that enough now, and I'm sure you saw it a lot in thermodynamics. One thing that can happen, doesn't always happen, but sometimes there are immiscibility regions beneath them. So this is a possible liquid immiscible space. Possible. Meaning not all pairs have this, okay? So I'm not trying to say it always exists, just sometimes it exists. Immiscibility beneath paper. Just so that we're all on the same page, this is liquid, this is vapor, and this is the VLE. Okay? But then we have a liquid-liquid equilibrium happening here. What does that mean? I'm going to get into it in more detail. We're going to talk about it a lot for the rest of this lecture and all of next lecture. What does that mean? Liquid-liquid. What? Just tell me what's happening there. What does immiscibility mean? I'm going on. Yeah.
There's just a separation between the dishes. There's
Okay.
two
Right.
phases.
There are two phases. Two liquid phases. We all see an example of two liquid phases. I guess it doesn't. I'm thinking about this, but like oil and water, right? You get two liquid phases that don't mix. I guess salad dressing nowadays mixes. They must put a emulsifier in them. They used to have to shake them. You guys shake vinaigrette sometimes? Anyway, why do you shake vinaigrette? Because it's oil and water. Okay. All right. So let's review immiscibility. Okay. So let's just talk about the bottom region here. This is X. If I have a material at T1 here, and the overall system has this composition, let's say it's 50-50, of two liquids, two components. Got it in a glass bottle. It's ambient temperature, it's a normal temperature, ambient pressure. What do I see? There's a subtlety here. There's the obvious answer, and there's a little bit more. It's not that hard. But what do I see? It's in a glass bottle. What is in there? Go ahead.
Meniscus?
No, not trying to be that tricky. It's basically the answer I already had before.
Phase
Yeah.
separation?
Go ahead. Go ahead. Yeah.
Boundary between the two phases.
There are two phases, but now tell me the composition of the two phases.
It's both, you said it's 50/50.
No, that's like, okay. So 50/50 is the overall composition of the mixture.
Oh, okay.
What's the composition of the two phases? This is something we have to think about with miscibility. Yeah, go ahead.
Almost 100%.
No, in the way that I've drawn it. Go ahead.
It's on the tie line.
It's on the tie line. So this is going to be phase, let's say phase 1, phase 2. Let's call this component A and component B. Okay, so this is XA. This is going to be the B-rich phase. Okay, and the composition of the B-rich phase is, in this case, looks like 25%. And this is the composition of the A-rich phase. Okay? So I'm not quite sure how to label this, but we have two liquids. And this is true for oil and water, although you never even thought of it. There's a little bit of oil in your water, and there's a little bit of water in the oil. Okay? They're both slightly soluble in each other. The way that I've drawn this, what's the solubility of A and B? This. What's the solubility of B in A? This. So our A-rich phase still has a little bit of B in it, and our B-rich phase still has a little bit of A in it. Does that make sense? Two phases, compositions are given by the tie line. It's exactly the same as when we did this. We have two phases. We have a vapor and a liquid. Here's Y, and here's X. Right? Our bubble point and our dew point, same thing. Let's call this X1 and X2, or maybe if I call it XA and XB, it's going to get really complicated. The point is I have two phases, both liquids. One has one composition, one has the other. Okay? If you have complete immiscibility, you're going to get a tie line looks like that. Okay? It's going to go right to the edge. But the way I drew it, there's some solubility of each in each. Does that make sense? Make sense? All right. Now, heterogeneous. What happens if we put this a heterogeneous azeotrope? This is a homogeneous azeotrope. Let me draw you a heterogeneous azeotrope. TXY, they're tricky to draw. Okay? Alright, this is a day of puzzles. Okay. What does this picture mean? I think you've seen it before. So now we're going to do separation with it. And believe it or not, describing the picture is the hard part. The separation is easy. Believe it or not. Separation with this system is easy. It's actually almost as easy as binary, believe it or not. The hard part is understanding the phase diagram and what's going on. If you want to describe it, someone tell me what's going on in each region. It's a phase diagram. If you use phase diagrams, we're going to have a lot. When we get to crystallization, well, they're going to be quite complicated phase diagrams. Yeah, go ahead.
So, in the top section, that's pure vapor.
Yeah, thank you.
And then in the two kind of triangle sections, that's vapor and liquid one and vapor and liquid two. In the kind of square section, it's.
What if I just do vapor? Yeah, you're right.
That's your liquid in the square. And then pure liquid one, pure liquid two.
Fantastic. Okay. One liquid phase, two liquid phases, vapor, liquid, vapor, liquid, vapor. Notice the similarity. All that's happened here is they've touched. Okay? Some systems don't have this. Some systems do. In some systems, they touch each other. Okay? Thermodynamics. All right? That's just the nature of it. Now, here's the puzzle part. I'm going to take a mixture of my two components. Let's call it B and A again. And I'm going to heat it. I'm gonna heat it in a glass vessel, even though we probably shouldn't. And I want you to tell me what you see. I want someone to volunteer to describe what you see in that glass vessel as you heat it from that low temperature where you have that first point, point 1, up to the high temperature. Let's just do start and end. You have some points in the middle. Anybody feel brave? I'll help you through it. Some of this is straightforward. Some of this you figure out. If you feel brave, I'll help you with that. Go ahead.
So it starts to form,
We're right there. What do you see in the vessel right now before anything happens? We're not adding any heat.
2 liquid phases,
2 liquid phases. What are their compositions?
pure liquid 1, pure liquid 2,
No.
or really close to it.
Actually, tell me where it is. I know I didn't draw this quantitatively, but what are the compositions based on my diagram?
It's going to be 99%.
No, I didn't draw anywhere near 99.
Wow.
Go ahead. Yeah, just help him. Tell me your name again.
Dexter?
Dexter. I'm going to come back to you, Dexter, okay? Help him out. Where were you? Yes, please.
Like 15 or?
Yeah, well, don't estimate. Just tell me how you got it.
It was where if you drew the tie line and then went down
Okay? So the 2 liquids have those compositions. Okay? This is going to become important. Okay? So it's important you understand that those aren't pure A and pure B. We have a B-rich liquid and an A-rich liquid. And that's the composition. Yes, you were guessing. It's like, but I'm making this data up, so its numbers are, okay? Dexter, go ahead. So now we've got a mostly B liquid and a mostly A liquid, but with quite a bit of each in each one, sidewalls in each one. I'm going to heat it. Do the compositions of those phases change?
Tiny little bit.
Tiny little bit. Good, that's the answer. So those tie lines, as we heat this, because this is curved, those compositions are changing. Okay, in this case, we're getting a little bit more B in that A phase. Okay? What happens next? When I hit the temperature of the azeotrope.
The liquid phase 2 is going to separate completely out of liquid phase 1, and you're going to start to see a
Go ahead. What happens?
Bubble
What's
point?
the first? A bubble. What's the composition of the bubble?
bubble has
Composition of the bubble. Anybody want to guess what the composition of the bubble is? Go ahead.
Below the azeotrope.
It is the composition of the azeotrope. So we get a bubble at X azeotrope. But it's just a bubble, okay? We've only just added enough heat, the temperature's right at the azeotrope. What's the composition of the liquid around the bubble? Yes?
Is it the opposite line of the azeotrope, so where the line to the left?
Yeah. Easy, mean?
Yeah.
So those 2 points, we still have 2 liquid phases. So when we're at azeotrope, how many phases do we have in this system? Yeah, not 4. 3. We still have our B-rich, our A-rich,
Oh, yeah.
and our bubble at X azeotrope. Now we're going to keep adding heat. What happens to water when it boils? You add heat, what happens to the temperature? It stays the same. Okay, so just get used to this. This is not a heat diagram, this is a temperature diagram. So I can add heat, the temperature stays the same. What happens as I add heat? Dexter, you have a guess at this.
you start to move up that.
I'm not moving anywhere. I'm still here. The overall system is still right there. I'm adding heat. What do you see in my glass container? Go ahead.
Boiling of the lighter component.
No. No. Believe it or not.
So 2 liquid phases mixing.
No. Yes.
The right liquid boils up.
No. Wow. This is good. Okay. Back then.
Stays the way it was.
Doesn't stay, because we're adding heat. So what happens when
But the temperature isn't changing.
temperature's not changing, so we're adding heat.
So it's staying where it was when we first got your azeotrope, wasn't it? If your temperature's staying at the
Yeah.
temperature.
We see
More bubbles?
We see more more bubbles, okay? So at some point, we're gonna start moving up into here. And as we move up into this space, what happens? We're gonna lose what? Actually, hang on a second. I think I'm wrong. I think you guys are right, and I was wrong. Show it to my notes. Oh, okay. Okay, so one of you said that the light, the A phase disappears. The A phase disappears. Okay, so we lose, the compositions don't change during this boiling up period. We get more and more vapor, and this phase disappears, but the composition doesn't change. If you have three phases, how many degrees of freedom do you have? Temperature's fixed, pressure's fixed. 3 degrees of freedom, anyone want to guess how many, three phases, how many degrees of freedom you have? You actually have 0. You probably haven't seen that many 0 degrees of freedom spaces before, but at 0 degrees of freedom, you can't change composition. Okay? So all you can do is change the amount of each phase. So we're actually going to lose this phase. We're going to get more vapor. So the bubbles are going to get bigger, which is what I was saying. And this phase is going to disappear. And once that phase completely disappears, then what happens? So that phase is going to boil off. And then what happens is we start to move up. Now the temperature will increase, because now we only have 2 phases once that phase disappears. What happens is we start moving up here in temperature. The composition changes of what? Vapor and liquid. And it's just a tie line, just like over there, which we're used to, I hope. Okay? So, I think, did you say the light phase boils up? Okay. So similarly, just to reinforce and correct my mistake a little bit, I'll let you help me since you tell me your name.
Brandon.
Brandon, okay. So if we start with the composition here, it's above the azeotropic composition. Again, here I'm going to have a mixture of an A-rich phase and a B-rich phase. Which one am I going to have more of, do you know?
A.
We're going to have more A-rich phase. Okay? And actually, it's just a lever rule. So the ratio of this to this is the ratio of the 2 phases. Okay? As I heat this, compositions change, and when I hit this point, I get 3 phases. And then what happens as I continue to add heat at that temperature? This is where it gets tricky.
Other phase start.
The other phase disappears.
Yeah.
So this phase disappears until I'm left with just the azeotrope in that phase. And then once I have 2 phases, then I'll move up into the VLE space, and then out to the vapor space. Okay? So this, moving in this direction, is just like what you're used to here. Okay? Yes?
So it goes up to the line, out, and then back in, and up again?
So you actually just move straight up the line. Okay, it's just what's happening if you're looking at it. So as you move up here, the liquid compositions are changing slightly. So those 2 compositions, you get stuck there. Then all of a sudden you'll get a bubble. And that bubble's going to grow, you're going to get more and more vapor as, if we're moving up this line, not this one. As this phase disappears, you have these 3 compositions. You're adding more and more heat, temperature doesn't change, just have these 2 coming, and it's going to get, the bubbles are going to get bigger and bigger and bigger. Composition of the bubble stays the same, the 2 liquid phases stays the same, until that phase disappears. And now I have that liquid and that vapor, and now I move up the tie lines in the vapor liquid space. Does that make sense?
Yep.
And so, if you're coming up here, the opposite happens. It's going to, we get, again, the vapor, 2 liquid compositions, but then this phase disappears. Okay? Makes sense? Now, can I teach you how to do separation units? Okay. Yeah.
Would, when you hit the azeotrope, would the liquid composition of, actually, I'll wait till after class.
Okay. Yes.
Is there a disadvantage to separating heterogeneous azeotropes? I feel like it kind of separates
kind of answering the question. Just hold on to that for, I got 5 minutes, I'm gonna try to get through it, okay? Tell me your name. Patrick. So, I can't actually separate with distillation. Okay, so this is one of the tricks by heterogeneous. I have to introduce a new technique. Do you know the name of it? Or if you don't know the name of it, could you describe how it would work, what it looks like? I'm going to get past the azeotrope because I'm going to use a trick of heterogeneous. It doesn't happen with homogeneous. It's the answer, it's your comment that you made to me. Do you have an idea what that device is called, what it looks like? I have to introduce a new device. It's very simple. Think salad dressing. But the opposite. I don't want to mix them. Yeah, but it does what? It splits the two liquids. So I'm going to make a device that's just going to split the two liquids by density. And I'm just going to get a light and a heavy liquid phase. I don't know, draw something like that. Does anybody know the name of that device? It's a decanter. Okay? So we're going to add a new device that's going to allow this to be, I'm guessing you're seeing something very simple about this, right? So let's do it. How is the simple thing going to work? Do you have an idea? We still want to get, notice there's only one place that there's pure A and pure B in this diagram. Where do we have to get pure A and B? Can we use just a decanter? When we're in the liquid regime, so beneath the azeotrope, is there any way to get pure A and B? So we can't decant to pure components. What do we got to do to get to pure components? Do you see, there's a way to get to pure components, and you should already have a clue. Say it. I heard someone whisper it. Say it loud. I still can't tell who's answering, but anyway, yes, the answer. Distillation. But now the question is, we need distillation to do this. Tell me how to hook it up. It's the third puzzle today. How do I hook this thing up? I need a decanter and I need a column, at least. Maybe some mixture of those. Maybe that's not enough. Any idea how to hook this whole thing up?
Well, like a normal column, and then after the condenser, put it through a decanter.
Okay. After the condenser. Okay. Let me look at the answer because sometimes this gets a bit. I'll make sure that I don't do this wrong. Okay, so I'm going to condense it. I have to reflux something, so I'm going to reflux it. Your name is?
Bill?
Bill. Okay, so I have to the condenser. What I'm putting in is the feed. So this decanter, what temperature am I going to have this at? It's kind of obvious, I hope. Think binary azeotropic distillation, which we never could get anywhere to compressed shift. So just remember back to that. What's coming out of the top of this column? What's the lightest thing in this system? Is it A, B, or what's the third choice? The azeotrope. So if we're at the azeotrope, what's coming out if I cool it all down in a condenser? No, I'm not coming to saturated, yes.
The
Liquid phase, what are their compositions? You don't know, don't give me numbers, just where are they? Yeah, go ahead. Go ahead, you're right, I think. Yes? No?
What were you asking?
I'm asking the woman in front of you. You were pointing. Go ahead. What's that?
Straight down from the azeotrope.
Straight down from the azeotrope? That's the vapor composition, but after I condense it, which is what's happening there, which I think Bill intuitively suggested, which is correct. The vapor, yes, is going to have that composition. What's the liquid if I condense that vapor? Yes?
It's gonna have the
You're right.
the left of that.
It's actually going to have that one and that one. Okay? So we're going to have those two compositions here. What are we going to do with them? Okay, better yet, let's come out of the bottom this column? Bill?
A stream to the reboiler?
All right, someone help me. Let's make this easier. What's coming out of the bottom of this column? I'm going to run over by a minute, but I think we're almost there. I know I was going to say we're almost there. We are. What's the feed? Good question. Well, we'll get to the feed. The feed will be obvious in a second. All right, tell you what. What are the two materials in here? I just told you. It's this composition, there, and that composition, right? The tie lines at that azeotrope. What do we do with them? Any suggestions? It's the answer that we all like. No. Yeah, okay, fair enough. Yeah, we're going to separate them, but we all liked it, but we've got to, rather than throwing this away, this is useless right now, right? What are we going to do with it?
Reflux.
What's it?
Reflux.
Not reflux, it's a reword. Recycle. How about if I take this one and I do this? I know this looks crazy. So what if I put this composition as the feed to that column? What's going to come out of the bottom? Say that loud. Pure B. I need one more thing to make this work. I need two more things. I need an overall feed, so it doesn't matter what composition I'm putting in, I'm going to put it in there. I need one more thing to make this work. What do I not have? A. Tell me how to do it.
Another column on that side.
Another column. What's the feed to this column?
Top,
Second part.
Say that loud.
top phase. And
The top phase. What's going to come out the... What do I do with the top of this? Going to put it in a condenser. What do I do with the stuff that's going to condense? What's the composition of the condenser coming out of that column? Say it loud, that's right. The azeotrope. But if I condense the azeotrope, what do I get? What's that? Liquid. I get the same stuff again. It's coming out of the bottom of that.
Pure.
See, I told you we were close. Now I know. I now need like 5 minutes for you all to ask me questions. How does that work? But it does. Okay? So, does anybody want to ask that question? No. I'll see you on Thursday.